chemical properties of elements are largely determined by the number of valence electrons that they contain. The element properties vary in a periodic fashion because the number of valence electrons varies in a periodic fashion. And thus the quantum mechanical model explains the reactivity of hydrogen and the inertness of helium and many other observations by looking at what are the valence electrons, how many of them are there. So for the noble gases, helium is going to have 2 valence electrons. The rest of them are all going to have 8 valence electrons. It turns out that's an especially stable situation. All of these are very stable elements. Very stable things, lower energy, they do not react easily. For many years, it was believed that there were no compounds that were formed. Now we do know they do form some. So this, in chemistry land, these are like the really cool kids in high school, the in-group that everybody wanted to be like. And so then you've got elements just to the left on the periodic table, things like chlorine. And chlorine's really close. Well, fluorine is next to neon. Fluorine is really close to being just like neon. The electrons, remember, on the outside of the atom, I think of those as being a little bit like our clothing, how we look, right? You can change your appearance. You can't change who you are. You can't change the number of protons, but you can change the number of electrons. And so what will happen is things are going to react in a way that they will obtain 8 valence electrons. So the alkali metals, you can really think of the periodic table as it really should be more of a circle, like a cylinder, because you're going around in kind of a spiral. So right after helium is lithium. Just has 1 more electron. So lithium is like, man, I am really, really like helium. I just got this 1 extra electron. So lithium will react very easily to lose 1 electron, and then it has the same electron configuration as a noble gas. Potassium has 19 electrons. Argon has 18 electrons. If potassium loses 1 electron, it's going to have the same number of electrons as argon. I really need a periodic table over there. Here it has 1 valence electron. When you peel that 1 valence electron off, what's underneath is a full valence shell. And that's what everybody is wanting to get. So these form positive 1 ions by losing 1 electron, and in doing so, they have the same electron configuration as a noble gas. The alkaline earth metals, group 2, they all have 2 valence electrons. If they lose those 2 valence electrons, they have the same electron configuration as a noble gas, 8 valence electrons. And so they are likely to do that. They react fairly easily, and they always form +2 ions. The halogens are on the other side of the noble gases. They're just shy. So fluorine just needs 1 more electron and have the same number of electrons. So it could either lose 7 or gain 1. Gaining 1 is easier. And so all of these are going to form -1 ions by gaining an electron. In doing so, they then have the same electron configuration as the nearest noble gas. So these are the ions that form predictable, elements that form predictable ions. So group 1, all +1. Group 2, +2. You know, we've been over this in terms of nomenclature, but we didn't understand why. So fluorine gaining 1 electron has this electron configuration. For oxygen, it has to gain 2 electrons, 1, 2. Nitrogen has to gain 3 electrons, 1, 2, 3. We've wondered about carbon. Why don't we see carbon ions? Well, carbon would have to gain 4 electrons. That's a lot. Or lose 4 electrons. And so carbon tends to do neither. He's like, you know, the nerd that's just decides I'm going to just be happy with who I am. I'm just not even going to try. I'm just going to do my own thing, right? So that's carbon. So we see these patterns, and it's because of the electron configuration. So aluminum. Aluminum loses 1, 2, 3 electrons and becomes like neon. All of these guys lose 1 electron, they become like the noble gas. So everybody's trying to be like a noble gas. Any questions?